Okay, we have for today's VQMS, we have George who'll be talking to us about the challenges of simulating large language models. This is our first LLM paper, I guess, in this seminar series. So I'm super excited to hear what George has to say about this process. Take it away.
Thanks for the introduction and very honored to be here to present the first paper. So we're going to talk about the challenge of using large language model to simulate human behavior from a causal inference perspective. This is a joint project with my amazing co-author Olivier Toubia. So we're really looking forward to your feedback since we're working on a revision. The motivation for this project is that large language model have demonstrated impressive potential to simulate human behaviors. It has been used to simulate a range of human actions, mimic human subjects in behavior experiments, simulate demand curves and conjoint analysis, create input for perceptual maps, estimate intertemporal preferences across languages, and also generally can be thought of as a potential collaborators for marketing research. And in other domains in political and psychologies, it has also been shown that it has impressive potentials in terms of simulating human behavior. So a realistic simulation of human behavior would be very valuable if it is very realistic. For researchers, it means that we can test theories and hypotheses about human behavior at a relatively faster pace at a lower cost. It also means that it's possible to evaluate scenarios where it would be otherwise difficult or impossible to conduct real-world experiments because of either cost constraint or ethical constraint. For firms, it's also very valuable. It's valuable for them to design and test new products, services, and strategies. Because if they have a certain ideas about a product and they can evaluate humans' potential choice immediately, then that would be very effective. It's also going to be helpful for them to understand consumer preferences and behavior, predict market outcomes, and also evaluate policy and regulation impacts. So a realistic simulation of human behavior would be very valuable. And many firms, and especially a lot of startups, have actually already are offering this large language model based customer insight services. For example, this is the front page of synthetic users, which is one player in this domain, where the way that they pitch it is that user research without the users. So where you can run your user and market research with the most human-like AI participants. And here is another example by evidence.ai, another player in this area, where they say we survey AI copies of your customers to build a finance-friendly sales and marketing plans in minutes, not months. So the pitch they have is that they can help understand the customer's preference like faster and also at a lower cost. And this is another company, Civic Sync is an AI-powered solution to conduct instant market research and surveys via digital replicas of real human beings. So a lot of companies and especially startups are offering services. And we have also talked to some startups and they told us that they already got some deals and millions of dollars of revenue deals from large companies that are interested in using such a service because it is less costly and also they can get results faster. So there's already an increasing adoption of this potential way to simulate human behavior in the industry. So at the same time, if we take a step back, we can see that many useful applications are related to causal inference in the sense that they involve simulating counterfactuals. In the sense that we are interested in changing the treatment while holding everything else constant. For example, what would happen to sales if we increase prices? What would happen to an ad if we frame the language differently? What would happen to the market if we introduce a new product or any other kinds of potential interventions that you can think of are related to this counterfactual simulation where we're interested in changing the treatment while holding everything else constant, what is going to happen. So our research questions are, what are the causal challenges in using large language models to simulate human behavior? What are the trade-offs between different approaches to addressing these challenges? And how can we improve experimental design practice for large language model simulations? So So we want to focus on the causal challenge because like we are aware that like of course the quality of the simulation depends on the input of the quality of the input data, and there has been already a huge literature documenting how the large language model may give biased results when the input data is biased. So we want to focus on something else, like suppose that the quality of the training data is okay. Are there other additional challenges? And the reason that we say that is because there has already been some established experimental design practices for simulating actual human subject experiments. But when we move things from actual experiments to simulated like GPT experiments, do those classic insights on what constitutes a good experiment still hold in these scenarios. So this is our research questions. I will pause here in case there are questions. All good? Okay. So here is a preview of our results. So when the large language models are blind to the experimental design, the model can create unintended association between the treatment of interest and other unspecified variables. And because of this unintended association, the simulated data in some scenarios may resemble observational rather than experimental data. And we're going to demonstrate that using demand curve estimation as an example. And the key trade-off here, in terms of why it is challenging to resolve this issue, is that if a pretreatment variable is unspecified in our simulation exercise, then it may be changed by the treatment assignment. But if a pretreatment variable is specified, it may become artificially salient and change the simulated decision process, in the sense that if you specify something, then the simulated individual may pay close attention to that thing, which may not be what you want to simulate initially. So there is this trade-off between unconfoundedness and ecological validity when we are thinking about designing a large language model simulation. And some lessons is that we need to reconsider many established experimental design practices for large language model simulations and potentially make the model non-blind to the experimental designs, like even though blinding is regarded as one of the good classic experimental practices. Okay. So let's get to some more concrete examples. So first, I want to just highlight that most attempts to simulate human experiments with large language models have been focusing on blinded designs. So this is like what a common blinded between GPT session design looks like that mimics traditional between subject experiments. So where each subject is a new independent large language model session, and different sessions will be exposed to different prompts or treatments. And this is like human studies to some degree, in the sense that the subjects are not blind. The subjects are blind to other treatment conditions or the purpose of study or the experimental nature of the variables that are being studied. So, for example, so this blinding has a lot of benefit in real experiments because it can reduce demand characteristics. It can better mimic real world conditions because in the field, when people are making decisions, they're usually only been exposed to one treatment, and they're unaware that in experiments. And at the same time, blending has a limited downside other than some practical constraints, such as that we cannot estimate individual level treatment effect when each participant is only receiving one treatment. And we may also need larger sample size. And sometimes it can also be unethical to not disclose that to the participants that they're in experiments. So in real world experiments, blinding has a lot of benefits. The downside is mainly related to practical constraints. But now in the GPT simulation, the question is like, what is the real downside? Because like the sample size is cheap in GPT, and also there is in comparison smaller ethical concerns. So does that mean that we should do blinding all the time for large language model simulation? So the key argument that we will have is that we'll show that blinding can lead to confounding. Any questions? so far? Okay. So I think it's useful to first go to the real world experiments to see like what kind of when there are blindings, when there are unspecified variables, what's going to happen. So consider such a price experiment scenario. A customer of unknown characteristics and history is in a certain context with unobserved detail. We don't know a lot about the customers. We don't know what the context is. We don't know in the sense that we don't have 100% of the information. There are still some things that are unobservable out there. And the customer is exposed to a randomized price of a certain product and makes a certain purchase decision. And due to randomization, treatment should be uncorrelated with pre-treatment variables, even if these pre-treatment variables are observed. And so usually we do a balance check to see whether the covariates are balanced across conditions for the observed ones. But even for the unobserved ones, because of randomization, we should expect that those pre-treatment variables will be balanced. But this becomes possible, this correlation between pre-treatment variables and treatment assignment becomes possible in large language model simulations because individual units and their context do not pre-exist. So when they do not pre-exist, they could be subject to change. And let me give you some more examples. So the empirical context we're considering is demand simulation, a classic problem where there has been a lot of causal inference challenges, such as like different kinds of endogeneity issue. So for this exercise, we selected the top 40 consumer packaged goods categories from the paper Delavinia and Jensko. And we focus on top selling products according to Walmart.com. And we want to stimulate demand for these 40 products. We are interested in the counterfactual scenarios in terms of what's going to happen when we set the prices to be, let's say, like 0%, 20% to 200% of the regular prices. And the simulation approach that we're using is similar to the between subject blinded design that we discussed before. In this exercise, we used a GPT-4o mini that is pinned on GPT-4o mini 2024 July 18th to help reproducibility. We set the system portion of the prompt to be you AI are a customer. Your task is to fill in the blanks, return the completed information in comma-separated values without any extra text. So the later part is just to ensure that the format can be easily processed. And then we are going to describe the purchase scenario and ask for purchase intention. We are going to set the temperature to be 1 and replicate it by 50 times, and then take the average to calculate the average purchase probability for all the products at any given price. So this is the setup for our simulation exercise. So this is a more detailed prompt that we're using in addition to the system prompt. So that's in the user part, we asked, please consider the following product category. Suppose you're in a grocery store and you see the following product in that category. We're also going to ask some questions that are related to unspecified pre-treatment variables. Because the idea here is that suppose we want to run a experiment that randomizes the price. We may want to check whether it's going to affect other pre-treatment variables and whether this is a balance. So we asked the last time you purchased this product, it was priced at a certain value, and then the product is currently priced at a certain value. So ideally, if in real world we say we observe customers past purchase price, and then we run an experiment, we should expect that the past purchase price of the customer to be balanced across conditions. So regardless of whether we are assigning prices to be high or low for like the customers, when we observe that their past purchase history, we should expect them to be balanced. So that this is like a history is a pre-treatment variables. We should not expect that to be affected by random treatment assignment. But when we ask this in GPT, this is what we found. So we see that there is a positive correlation between the price, which is the treatment variable that we are randomizing, and the past price that the customer used to make the purchase. So we see that there is a positive correlation here between the current price and the past price. And similarly, we can extend this analysis to other variables. We can also test it, like what about the competing price? So this is the price that is randomized, and then the competing price, similar products that are from a competing brands in the same category. What about the price? We also see a positive correlation, and also the expiration dates of the product is also going to be correlated with the price. So there is this correlation between the treatment of interest with other variables, even though initially we may not expect this correlation.
Sorry, George.
Yes.
Can I ask?
Yes.
Ima, go ahead.
Yeah, just a clarification question about what is actually intervened on. So if you go back to the prompt, the one in red, that's randomized, right?
Yes. Yeah. Across different sessions, we assign different values of price.
Okay. And the thing that you're saying, which is not randomized and correlated with treatment, where does that show up? Is that the return? Is that in the return example?
Yeah, it's in the so we first give an example, and then like in the answers that they will return a number, and that we visualize the correlation between the price that is randomized with the other variables. Yeah, and we try this with the last time you purchased, and we also try this with the competing price, the expiration days, and we also tried a version where we ask many questions at the same time, and then randomize the price, and then we find that this correlation between prices and other pre-treatment variables are consistent across like different exercises, that we see that there is this positive correlation.
George, can you help me think about history here? History could be looked at it like two ways. One is within a person, so the responses are somewhat consistent. So within a synthetic person, responses are somewhat consistent. But the history is also across people, right? How do you preserve history within a person? That seems reasonable that you would want to do that. But then also making sure that their history is not preserved across people. Does that make sense?
The histories are not preserved across people. Could you elaborate on that?
Yeah, basically that each synthetic person is a random draw. You want to ensure that each person is independent of the other synthetic person.
Yes.
But within a synthetic person, the answers kind of need to hang together. So preserving that history seems like a good thing.
Yeah. So I think it depends on what we want to do. So if we think about like standard experiments, suppose that the firms observe the past history of consumers. And for standard experiments, we should expect that a valid experiment would ensure that the distributions of those histories in the treatment condition should be the same as the distribution of those histories in the control condition. So that should be a criteria for us to ensure that the experiment is valid. And if we're interested in like a causal question in the large language model scenarios, we may also want to ensure that the distributions of those historical variables should be balanced across conditions.
Thank you.
Yeah.
George, so this might be somewhat naive, but what if you just tell that you are in an experiment, we're trying to figure out price. This is, but then would it learn not to have this association?
That's a great suggestion. That's going to be like part of our like solution framework here. Like part of the solution could be considering the possibility of actually revealing to GPT that they're in experiments, and we're going to discuss some of the promising aspect of that. But also there are some issues, at least with the existing model. And one is that actually, if you tell them the context, they will use that as additional information to make some inference, but yeah, we'll get to that later. Yeah.
George, I think I've just hung up on something very basic. This is probably just me. So I thought the previous slide, I thought you're randomizing, product and price and look at the purchase intent. And here it seems that you're looking at LLM's inference of the previous price based on the current price.
Yes.
Is that?
Yes.
but shouldn't, like, why should we expect no association if that's the inference task?
Yeah, so that's a great point. I think that's what I want to get to next. So in hindsight, like we should expect no association. We should expect, and that's precisely like the challenge here, is that in real observational data, the price of the focal product should be in form of the price of the competing products as well as the past price in the stores. And if a large language model is trained on such data, then like without additional like constraint or instructions, they would also naturally make this association, right? So like it is natural for, unless we give specific instructions, then like because the large language model is not a causal model, it's a predictive model. It's going to give the best predictions. It's going to give the best predictions of the competing price and past price given the current price. But from a experiment perspective, if we're interested in using the large language model to simulate scenarios where we change one thing while holding everything else constant, then that becomes problematic.
But that task itself, if you just feed it to a human, I would expect there to be association as well, right?
Yes and no, I would say. So yes, for human, they may make association in terms of belief and memory. For example, if they're experienced with the current, if you present them with higher price, they may believe that the past price is also high. They may believe that they may remember that the past price is high. That is possible, but like they will not like change the actual history of the past price. So the scope of the problem is different. Yeah, so the set of variables and the degree of inference could be different.
Yep, thanks.
Yeah. Other questions? Okay. Yeah, so this association is not surprising in hindsight, and in fact, sometimes this association can be very useful. All right, it's useful if researchers want to predict, like focus on predictions. What is the best, most likely competing price, most likely past price, most likely expiration dates, given the current price. For example, expiration dates, it's possible they will infer the quality based on the price. That's plausible. But it could be problematic if researchers want to estimate the impact of changing the focal price while holding everything else constant, like holding the competing price constant and holding the past price and the history, the context, and the product quality constant. So that is where it becomes problematic. Okay, next. And so we showed examples of demand estimation, but I just want to say that this phenomenon of unintended association could generalize to other domains where you want to use the large language model for simulation. For example, product recommendations. Think about when we are simulating customers' decisions of whether they are interested in a certain product when they're recommended a certain product. Then the recommendation themselves could be like endogenous in the sense that it can be correlated with customers' interest in the product. So this is like the classic like advertising endogeneity issue. And in other recommendation contexts, online advertising, book recommendation, this could be a general problem in the sense that when we are like changing the intervention, for example, like the advertising decisions or showing certain ads to customers, the model may infer that this is because that the customer is interested rather than this is they are seeing an ad that is being randomized. Yeah, I saw another. Iman?
Yeah, just conveying an audience question from Tong Guo. Are the correlations that you find in these domains comparable to the correlations in real world data sets? I think this is sort of related to calling it unintended associations, but like how do the GPT associations compare with?
That's a good question. So it depends on how we want to measure it. I think one way to measure it is just to I guess like one answer to that is that we have compared the results of the demand estimation result, and we show that based on the survey and based on our results, the answers are different. So at least based on the outcome variables, they're different. In terms of based on the correlation of the unintended variables, so this one is a bit tricky because by definition, when we are thinking about the randomization, they should the actual ground truths should be 0. That there should be 0 correlation between the treatment, the pre-treatment variables, and the random assignment. So this is the ground truth by definition. So like if GPT are making the inferences, then it could be problematic. And for the actual human, we haven't tested that, but I think this is something that we can further test, like in terms of the actual degree of assimilation. But it is like one tricky thing is like how do we distinguish belief memory versus actual variables? So because when we are using surveys, we are going to like elicit the customer's belief that indeed is going to be affected. But in terms of the actual history and the actual context or characteristics, like that could be a bit more challenging to document.
Thank you.
Yeah. Other questions? Thanks. Yeah. So so now what's gonna happen to the estimation of demand curve given this potential unintended assumptions? So again, here we are asking like what is going to be the purchase decisions given price. So we do not ask other unspecified variables, and this is the result. So if you look at it as price, when the price is very low, the GPT's simulated purchase decision is almost 0. As it increases, we see that there is a range where there is upward sloping demand curve, and then later as it goes down, we have a downward sloping demand curve. So to some degree, you can think of this as like in observational data, it is also possible that you will see a demand curve like this if it's not estimated properly, or there are no or there is confounding issues, like we see upward sloping demand curve in some regions because there are some unobservable that are affecting the price and demand at the same time. So this is like for GPT, we also see this this inverse U-shape demand curve. And a natural question is like whether human will also make the similar inferences. Like for example, when they're taking the survey, is it possible that they'll also infer that the quality of the product is low, the expiration date is low, the past price is also low, and they therefore make similar decisions. So we run a prolific surveys online that we ask for representative U.S. populations and ask the exact same purchase interest questions to human participants and compare them with the large language model. And each respondent answer like 40 product questions, 1 per product, with price randomized across respondents. And this is what we found. So for the actual survey, we see that the demand curve is almost downward sloping. We did not find that there is this invert U-shape, at least based on the comparison of the actual survey. So this is just to show that this is unlikely driven by like pure like biases that are also exist in the human. Okay. Any other questions?
George, I'm curious about if you look at this the demand curve after the first 2 points,
yes,
it is downward sloping, right? So it seems like the first 2 x-axis values, that's sort of where this violation is happening of the demand curve. And is there something an intuitive explanation for that?
One possible explanation, as we have shown before, is so one driving force could be that the competing prices are low, the quality is low, the past price that the customer have purchased the product is so very low. So that could be one driving force that that leads to this upward sloping demand curve. But I think it's interesting to think like why the the curve becomes downward sloping again. And that could be that. But here I cannot give a definite answer. I'm just speculating here that there are like another force is that the GPT still have this prior belief that the higher the price, the less likely to buy. So I guess that's but it's hard to say. It depends on which exact model you're looking at.
Got it.
But it was like a real experiment that an experimentalist is doing. They tend to do process checks, right? This is something you could actually certainly do for both humans and for the LLM. It's kind of a really weird result, right? So, but you could ask the LLM like, what were you thinking? Kind of, at least try to get some process checks.
So are you proposing this could be like one way for us to check like the validity and plausibility of the large language model simulations, or you're
just try to uncover the underlying rationale for why are you getting the result that you're getting for the LLMs when the relative price is at the bottom end.
This could be one way. We did not explore that direction because one concern seems to be that the model, the large language model, seems to have a lot of cases where they're rationalizing ex post. So that's why we're hesitant and unsure how to think about it when we directly ask them the reasonings.
Yeah, I mean, your quality conjecture was somewhat reasonable, I thought. So perhaps it's plausible. I'm not sure, but
yeah. Any other questions? Okay. So this is when we do not specify a lot of details, we get a result like this because of unintended assumptions that GPT are making. And a natural question is, we have this issue because we haven't specified those details. Can we specify those details to address this? And this is analogous to the controlling for covariate approach when we are working with observational data. So if the simulated data looks like observational, can we address this issue by controlling for them? And a common way to do this is to create silicon samples of synthetic personas, generate very detailed demographic profiles, specify relevant contextual variables, define pre-treatment histories. This can be the relevant covariates that could be included in the detail that if we have specified them, then maybe they will not be changed by the treatment assignment. And then after simulating the distribution of personas, for each persona, we can run the demand simulation and average across them to get the aggregate demand curve. So this is another approach that we have explored. But the key question for this approach is which variables should we include, just like in observational study, like which variables should we include and which variables should we not? And can we specify all relevant details to kind of satisfy the standard conditional independence assumption? And does adding detail does that introduce new biases? So these are some of the questions. Here is an example of what happens when we add demographic variables. It slightly improves the results in the sense that we no longer see that the customers are not making any purchase when the price is zero. But it also does not fully resolve the issue in the sense that we still first see that there is a gap between the model and the server results. And secondly, there is still an area where there is an upward sloping demand curve, which suggests that like for some customers, they still like make the choice that when it's lower price, they are less likely to purchase. And this is for consumer packaged goods. This is not for luxury products. So this is also another piece of evidence saying that this does not empirically fully resolve the issue. We can also try add more contextual variables. So here is an example where we add competing and test prices. If we're evaluating the demand curve based on whether it's downward sloping, this seems to improve the results. So here we're specifying like the store level price history and also the competition price, and this leads to a downward sloping curve. But as you can see from this curve, so here on the x-axis is the relative price, and the y-axis we're focusing on the Coca-Cola purchase probability for this exercise, and the dashed line is the store past price and also the competing price from competing products. So when we ask it this way, you see that the model and or the stimulated individual is placing a lot of emphasis on the variables that we're supplying. So like variables that are intended as controls were used as salient reference points by the stimulated individuals. So this is like the potential like concerns that you may have in the sense that in a real field, when individuals are making decisions, they may not always pay attention to all the available informations. They may not like pay close attention to the competing price. They may not be aware of what all the other hundreds of products, what their competing prices are. And they may also not remember the past price. But in the case of GPT, when we are controlling for covariates, it is unclear that whether they should be intended to use as a control where individuals are not necessarily considering them when making decisions, or they should be served as some salient factors that directly and strongly affect the individual's decisions.
Can you briefly talk about how you introduce controls? I'm assuming they're part of the prompt. And
yes.
If so, like what did it look like? Just a description of the personas.
Yeah, so we'll post that later in the paper, but yeah, this is a good question. So here, so remember in the original prompt, like we have something like the last time you purchased the product, it was priced at certain values, and we add this we add the additional information here in the prompt, and then we ask the purchase information. So similarly, we asked, so please consider the following product. You are a customer with a certain demographic variables, and then we are going to describe the last price and also the competing price. So in the prompt before we introduce the treatment assignment, which is the price, and before we ask them the purchase decision, we describe the additional information about the customers as well as the contextual variables.
Thank you.
Thanks.
George, just a couple of questions from the audience. I think they're both quite related. So first from Sriram. Sriram asks, if we elicit quality conjectures, can we use that as a control and tease out the effect of price? And I think you talked about that a bit on this slide. So that's the first question. The second question is, would it be possible to first ask GPT, what is the reasonable price for this product in this category? And then ask the same prompt you used, and then finally control for the GPT expectation of the price. So sort of two solutions that are kind of similar, where you elicit something from GPT, control for it, and then you use your actual prompt.
Yes, I see. So that's yeah, I think that's very very reasonable approach. Like one way to think about it is that it is similar to like adding variables, right? So here we are first like simulating the distribution of demographic variables and other variables about the consumers, but we can also simulate the customer's belief about the product given the price, and we can also like, well, what's the second one again? The second one was.
So you could ask GPT, what is the reasonable price for the product in the category?
Yes. So that could be some like additional variables that we're going to simulate, and that is going to act similar as the competing price and last price, in a sense that when we ask for it, they will play a heavy emphasis on it. So when we, for example, when we included the customer's belief about the quality, and when we included the customer's belief about the reasonable price, it is possible that they could be used as a salient reference point when making the decisions. So I think the question is, when we're interested in simulating human behavior, do we want to incorporate that procedures? You could argue that in some scenarios, if we have some strong belief about like how customers make decisions, for example, if they will first think about the quality and think about a reasonable price and use the reasonable price, like the internal belief about a reasonable price as the reference point, then that could be some reasonable approach that we can use in helping alleviate this issue. But if customers do not always think about it that way or do not always infer the quality, then that may not be sufficient in addressing this confounding issue. Yeah. Okay.
George, feel free to dismiss this is not kind of part of your scope. Have you thought about structuring things in like a conjoint setting where you're choosing among several choices?
We thought about it. We think that the general insights would apply. So it depends on whether we are thinking about like a between session conjoint setting or a within session conjoint setting, in the sense of whether we want to like make the choice, whether we want to ask multiple questions in the same session, or like if it's between session. If it's between session, then it may suffer from similar issues. In the sense that the GPT may make some unintended assumptions given the choices that are presented. Yeah. Any other questions? Okay. Yeah. So here I just want to like summarize a little bit of why like controlling there are some dilemma of adding control variables. So variables meant as controls could become decision anchors and can create some artificial decision-making process. And its success requires a double coincidence in the sense that first, the conditional independence assumption needs to be satisfied, like when we add those covariates. And second, this covariates should happen to be factors that consumers are hyper attentive to in their decision process. For example, if the customers are hyper attentive to the quality and they're hyper attentive to like the reasonable prices, and this variables happen to satisfy the conditional independence assumption after controlling them, then it's plausible that the conditional that this is a question that can be addressed, or like at least does not suffer so much from this this challenge. And so to Jenny's point, in conjoint, if we believe that those variables are the variables that the customers pay close attention to when they're making the decisions, and when we control for those variables, then there will also not be like other confounding factors that are affecting people's decisions. Then it's possible that in conjoint settings, this problem can be addressed. So if these two conditions are satisfied. And just to kind of compare, so for the real consumers, the main challenge is usually that they are inattentive or are unaware of the other variables. For example, they do not remember what the past prices are, or they do not pay attention to competing prices. But for the simulation, the simulated individuals may use these prices as explicit reference points. So this is the main tension here in terms of, if you don't add something, you may introduce confounding. If you add something, you may like change the decision process that may be different from what you are originally interested in studying. So here we also want to talk about like a theoretical framework to think about these things, because like a natural question is whether this is a challenge that can be resolved when we have better models, for example, more advanced models, GPT-5 or GPT-6. We argue that the challenges are unlikely to be fully resolved by merely improving the model or fine-tuning. And the key argument that we're making here is that no matter how advanced a large language model is, the answers cannot be reliable if the question or the prompt is ambiguous. So it can be like formally framed as an impossibility theorem that no large language model, regardless of its sophistication, can correctly answer causally ambiguous prompts that have multiple valid interpretations. So here we're thinking like a prompt is a P that has a lot of elements with variables x from x1 to xn, and the x could be, for example, prices, competing prices, past prices, qualities of the product, and the outcome could be the purchase decisions. And like we think that the large language model is a function f that like takes the prompt p as the input and will return a distribution of output. So no large language model f can satisfy this property of answering multiple answering causally ambiguous prompts if there are if this multiple causally if this ambiguous prompts have different answers. Let me give you some like more concrete examples. So suppose that this is the prompt, that we are supplying to large language model. So you are a customer who has recently read an article about how sugar consumption affects health. You are in a store and see two products, regular Coke. Oh, sorry, the other product's missing. Regular Coke, 39 gram sugar per ounce with a soda tax of a certain value. Would you purchase the product? So this prompt is causally ambiguous in a sense that it is unclear which variables are treatment and which variables are covariates. One possible treatment could be that this is the focal price. It's also possible that the soda tax is the treatment. It's also possible that whether the customers are assigned with an article about how sugar consumption affects health is the treatment of interest. You can think that there are multiple causal interpretations of this prompts. So the first one could be price is the treatment, and we're using the do operator, the notation here, where do is represented as like assigned a price rather than this customer happens to experience this price. So one possibility is that this prompt is trying to answer like what is going to be the purchase decision when the customer is assigned with this price and this customer happens to have this health information and see the sugar content versus whether this what is going to happen when we randomly assign this customer with like healthy article information and like who happens to see this price. So there are multiple causal interpretations, and the questions and the answers to these questions are likely to be different because, for example, customers who happen to see healthy articles are different from customers who are randomly assigned with articles, with healthy articles, and customers who happen to experience a certain price are different from customers who are randomly assigned with the price. So the answers to this causal questions are likely to be different. And when we think about fine-tuning, we can think that if the fine-tuned model is only intended to be used for one purpose and one purpose only, then it's possible. So for example, if the model is only fine-tuned to answer the question of the price of Coca-Cola as the treatment variables, then it's possible that fine-tuning can address that question. But when the fine-tuning is fine-tuned to only interpret the price as random variables and health information as a covariate, then it will not be able to answer other variables where, for example, what is going to happen when we randomly assign customers with healthy information or when we randomly change the sugar content of the product. So like a fine-tuned model may be sufficient if there is like a very specific dedicated use, but like for a general purpose model where could be a lot of different treatment of interest and different ways to use the covariates, whether it's a factor to be considered or a variable as a control without considering the factor. In that scenarios, it can be challenging for like fine-tuning to solve all these questions at the same time. Any questions so far? Yeah, so and here is an example, another example. We are comparing what is going to happen when we add basic control variables that we discussed before, including demographics and prices, versus when we also add that the customers have read an article about that sugar consumption may affect health. And in this scenario, you can see that again, when we add something, the customers may pay closer attention to the additional covariate. So here, when the customers pay attention to health-related factors, they overall are less likely to purchase. So this is again the dilemma of if you add some covariates to try to address the unconfoundedness issue, you may experience the issue of changing the decision process that the customers are making. So now, what are the potential solutions? This is going to be related to Jenling's point about what if we just tell the GPT that they're in an experiment. So we are considering like several solutions. We have considered also have a between session design where we are saying that the customers are in experiments, but the better results that we found so far is actually directly communicating the experimental designs to the large language model and ask it to predict the aggregate results. So because the GPT has the potential to like make good predictions, and if you're just supplying all the information that are available about the context or the survey details, including what the treatment is, what are the set of treatments that are assigned across conditions and the exact survey conditions, and ask you to provide the predictions of the purchase probability at each point. So at least in this specific empirical applications, we find that like communicating the experimental designs to the GPT model actually has better performance, at least in our example. So this is the results when we directly specify the experimental designs, and that it shows that gives some promising results. But of course, this one is not this approach is not without caveats. One caveat is that remember that one of the core issue is that GPT will make unintended assumptions or associations regardless of what information we provide. Here, if we are changing the set of prices that are being included as part of the experiment, then the GPT may also will use that as additional information to make the prediction. So the red line is a case where we kind of disclose that we are running an experiment that randomized prices from this 11 values, and the blue line is that we are saying that we are running an experiment that randomizes the prices from this 6 values. And in standard experiments, where we don't have to reveal the experimental design at all, we should expect that this 2 lines should overlap. But in the GPT simulation, when we are communicating the experimental designs, even though the original design performs really well, it is sensitive to what kind of information that we're providing. But so fortunately, we have also tried different versions of GPT. Like we tried 4.0 mini, which is our benchmark model, 0.1 mini, and 0.1 preview. We see that it seems that it is getting better at like correctly interpreting our instructions. We see that the gap between these 2 lines are decreasing, and suggesting that this could be a problem that can be resolved. So in terms of like whether GPT understands randomization or experimental design, and whether the experimental design should affect the outcome. So this front, it is possible that the GPT could like improve as we get better model. But for the problem of blinding, like when the GPT is unclear whether like what the treatment of interest is, and what variables should be used as a covariate, a factor to be considered, or a treatment, in that scenario, it is more challenging and may not be fully addressed by fine-tuning GPT models. So to summarize, the challenge of using GPT or large language model in general to simulate human behavior, one fundamental challenge is that in blinded large language model experiments, treatment can affect unspecified pre-treatment variables and create unintended associations resembling observational data. And the trade-off in the simulation is that is unconfoundedness versus ecological validity when adding controls, and cannot be fully resolved by better models alone. We want to also think about how to use them and what additional information to include. So to take a step back, one way to think about this is that if we think about the GPT or large language model in general as a predictive model, it's like predicting the next word, and blinding is like withholding informations from the model, right? If we think about like fine tuning, if we are not giving informations about whether this is experiment or whether this is observational variables, like whether this comes from experimental data, what is the source of variation. So if we're not including this information in the fine-tuning process or in the application process, then it's like withholding information from the model, which could lead to worse performance. So that's like one way to think about the role of blinding, and why that is not going to be exactly the same as the traditional experimental design. And promising direction could be that unblinded designs with explicit experimental specifications, but just to be aware that the current models still have a lot of limitations, that it may not fully understand like randomization or like the role of experimental design. And the best practice for a large language model may be different from human experiments. So that's our main takeaway. So thank you, everyone. So I'll just pause here for comments and questions. Yes.
Maybe I can start. So this was a very interesting approach. I was wondering if so there are a lot of public pre-registrations available online, like the AEA registry. And things like that. So what if I don't know if you've done this already, but you could take all of the pre-registrations, make the pre-registrations the prompt, which is the description of the experiment, and then see if GPT-4o Mini replicates the actual results in the paper, in the main experiment of the paper. And that would kind of, I guess, lend some validity to whether this is actually deconfounding the LLM. The problem is that these pre-registrations are probably part of the pre-training data.
Yeah.
And so, like, I'm wondering if it's behaving the way you're observing it to behave because of the fact that there are some pre-registered experiment descriptions in the pre-training data.
Yeah, I like this idea because beyond validation, like whether the existing GPT model is capable of predicting the results accurately, we can also think about using those pre-registration data and results as the training as a fine-tuning step, and see that if those experiments have a lot of generalizability, then it's possible that the fine-tuned model may also be good at predicting future experiments. But that's something that's worth exploring.
Yeah, exactly.
Yeah.
Thank you. I can. So Neeraj, you're a.
Thank you. George, in terms of framing this body of research that's emerging in synthetic respondents and experiments, where do you see it fitting? Do you see it as like a complement to what we will ask humans to do in experiments, or do you see it as some substitute, sort of like you're thinking a fair bit about it? I'm just trying to see how this fits in the grand scheme of things in your mind.
I personally want to think about it as a complement in the sense that it can be used as a pilot study, because at least but that's like just personal opinion. I'm not sure whether it's a good idea to 100% rely on the model simulation response, but in terms of using it as a pilot study to make the exploration and more efficient, if the simulation is close to realistic behaviors, that could be helpful. But the premise here is that the simulation is closer to actual human behavior, because otherwise it can be counterproductive in the sense that if, for example, the demand curve that we saw, if we take that as the ground truth, then it may not be as good as like not using them at all to begin with. So if the simulation is better or compared to human prior, then maybe it's an effective tool to run some pilot studies.
Okay.
I can convey a question from Tong, who asks, can we say that okay, cool. Yeah, I think it is similar to my question. So basically, the worry is that is GPT just summarizing the results of previous pre-registrations, so it won't actually be able to generalize to future studies. So I think that's a difficult question.
Yeah,
but
I think that's a valid concern. Yeah. The question is better. Like, suppose we have a predictive model where the training data is the results of the previous experiments, and if the model is good at predicting future experiment results, whether that is helpful or not. But we do have to worry about whether like we're in terms of novelty of the experiment results, and whether we're just conforming to past experiment results if we do something like that. Yeah.
All right, so we are at time. So I'm going to stop the recording, and this concludes the formal part of the presentation.